have so far applied Newton's second law to study a number of cases. Newton's second law says force equals mass times acceleration. In particular, if you know for sure the net force exerted on an object is zero, then there should be no acceleration for that object. That is, of course, provided that Newton's second law is valid. What is the condition for Newton's second law to be valid? Well, let's study this particular example. Suppose I have here a railroad car. It's pulled by a train so that it moves forward. Now, if it moves forward with a constant velocity, or if it is stationary, then if I consider inside the car, if I consider there's a smooth horizontal table, and on the table there's an apple. If the car is stationary or moving forward at a constant velocity, which means it's not accelerating, then what's going to happen to the apple? Well, the apple, just as the rest of the car, is undergoing no acceleration, right? It's either at rest or moving at a constant velocity, and the net force on it is equal to zero. It's just moving along with the rest of the car and the table. So it makes sense. No net force, no acceleration. Now, what should happen when the railroad car all of a sudden pulls forward with an acceleration? With an acceleration which I call A0. You can imagine common sense. From common sense, what happens as a result? This thing all of a sudden pulls forward with an acceleration, right? Now, if the apple is not to fall behind, it has to accelerate along with the rest of the car, which means the apple has to acquire an acceleration A0. But since the table is smooth and horizontal, there is no friction, static friction, that pulls the apple forward. So as a result, the apple does not have the ability to move along with the rest of the car. It's going to stay behind and it's going to fall off the table. Okay? Now, if you try to understand this phenomenon from a bystander's point of view, okay, if you stand by the side of the track, you look at that apple, you say, gee, that makes sense, because the apple is still subject to net force of zero. Nobody's pulling it forward with an acceleration horizontally. So that's why, as the rest of the car pulls forward, it stays behind and eventually falls out of the table. That's how you understand it. Newton's second law is still valid. But what if you are inside? You're inside and you watch this apple. Now, you see this apple moving towards you, right? You see this apple moving towards you with an acceleration of what? From your point of view, negative A0, right? And then the apple goes towards you at acceleration negative A0 and eventually falls off. So the question is, how are you going to interpret this phenomenon that you just observed? That the apple all of a sudden picked up an acceleration, moved towards you. Well, there are two ways to go. One is, you say, you know, Newton's second law is not valid anymore from my point of view, because if you try to measure the force on the apple, it is still zero, right? There's no friction. The table is completely horizontal and smooth. And yet the apple suddenly picks up a acceleration, negative A0. Okay, so you had zero force, and yet apparently there was an acceleration, negative A0. So Newton's second law is wrong. That's one way to explain it. Well, is Newton's second law wrong in this case? Yes, it is, because there is a condition for the validity of Newton's second law. How come this person sees Newton's second law still valid and that one does not? Well, the difference is that this person is using the railroad or the earth as a reference frame. The earth itself has negligible acceleration. So the reference frame, which he is using itself, has no acceleration. Okay, a reference frame that is not accelerating itself is called inertial frame. So basically, this is telling us Newton's second law is valid only in an inertial frame, which itself is undergoing no acceleration. From that person's point of view, that person sees Newton's second law is not valid anymore. And the reason is because he is in an accelerated frame along with the railroad car, right, which is accelerating forward at an acceleration of A0. That is why he would find Newton's second law not to be valid. And therefore, we must be careful when we can and cannot use Newton's second law. it turns out Newton's second law is only valid in an inertial frame, and it is not valid in an accelerated or non-inertial frame. Accelerated frame means the frame itself is undergoing an acceleration. Okay, it is otherwise known as non-inertial frame of reference. Now, that was one way to explain it. But you see, even though we can understand what's going on, we say, okay, simply because Newton's second law ceases to be valid in this person's frame. But this may not be a very convenient way to proceed, because after all, we live in a non-inertial frame, don't we? We live on Earth. You think the Earth is not accelerating at all? The Earth is actually accelerating. For example, the Earth is moving around the Sun, right? It's actually doing a near circular motion. It turns around every 365 days or so. So it is doing a circular motion or near circular motion. Of course, it is accelerating. Well, the good thing is that acceleration is pretty small. But another thing is, what about the spin of the Earth, right? Even if you sit on your couch doing nothing, in 24 hours, you're actually sweeping out a large circle, right? You're sweeping a large circle because the Earth is rotating, spinning at the rate of 24 hours per cycle. And therefore, we're doing, accelerated motion, right? Even though, these are pretty small accelerations. But the idea is a true inertial frame, which has no acceleration whatsoever, is very difficult to obtain. Okay, we live in a non-inertial frame. We often that it happens that we have to study a phenomenon which takes place in a non-inertial frame. Let's say, for example, a car making a sharp turn. Of course, that car is accelerating rapidly, and then how do you understand the phenomena from the frame of the car, which is accelerating? You cannot use the conventional form of Newton's second law because it's going to yield wrong answers, as you can see from this person's point of view. So the question now is there a way I can modify Newton's second law so that it still can be used even though we're living in a non-inertial or accelerated frame? Well, let's see what happens here. Look at this apple here. From this person's point of view, in accelerated frame, the apple is subject to no real force, right? There's no friction, no real force exerted on the apple. And yet, somehow the apple still manages to accelerate with an acceleration of negative a0. It is wrong to apply Newton's second law to this apple because we're using a non-inertial frame. But on the other hand, suppose I pay a price. Okay, I pay a price such that I can modify Newton's second law so it becomes valid. How would I do it? What kind of price I pay? Well, it turns out if this person believes somehow there is a mysterious force pushing the apple this way off the table, okay, that force is responsible for that acceleration, negative a0. If that person somehow believes that force existed, then he can still explain what happens to the apple because, after all, it's the force that gives that mysterious acceleration, negative a0, to the apple. The question is, does that force really exist? Of course not, right? There's no such real force. So it is not a real force, it's what's called a fictitious force. It does not exist. We also call it pseudoforce. Pseudo means it's not a real force. Pseudoforce. We can also call it inertial force because, after all, it is due to the fact that we do not live in an inertial frame of reference. All these names refer to the same exact thing. That force is not real, but we pretend that it existed. And that force would then, if you add it to conventional forces, would help us restore the validity of Newton's second law, even in a non-inertial frame of reference. So that is the price we pay. That is, we imagine a pseudo force that does not quite really exist. So how much is that pseudo force equal to? That pseudo force is equal to mass times the acceleration it provides, right? The acceleration is negative a0, and therefore you have negative a0, that is the acceleration, times the force, times the mass, that is mass. That gives you this mysterious fictitious force. F equals mass times the acceleration it produces. So let's add a subscript F0, just like here, A0. Okay, Again, this is not a real force. It is not gravitational. It is not electromagnetic, whatever. It has no real physical origin. It is an imaginary force. But with that imaginary force, if we add that force to the real physical forces such as friction, such as gravity, whatever, then we'll come up with a modified version of Newton's second law, which completely explains the motion of this apple even from an accelerated frame, which is the car itself. So, what is the modified version of Newton's second law? You add this force to the real physical forces. The original Newton's second law says F equals ma. Okay, F equals ma. Now, suppose in a non-inertial frame, I use a prime to denote that we're measuring the acceleration in a non-inertial frame. We call it a prime. Okay, and then it turns out to do so, we must add this fictitious force F naught. So I'm gonna add that into the mix, F plus F naught. This is Newton's second law in the non-inertial frame of reference, or accelerated frame of reference. So, for example, how do we explain the motion of this apple? Well, in that case, what is the real force equal to? The real force equal to 0, right? What is the apparent acceleration a prime measured from the accelerated frame? It's negative a naught, right? It's negative a naught. But what is the force F naught equal to? It's m times negative a naught. So you see both sides are equal to m times negative a naught. So it works out. Okay, so this is the price we pay to widen the scope of validity of Newton's second law. So we now can understand motion of an object even in a non-inertial or accelerated frame of reference. All we have to do is to add this fictitious force. Okay, we add this fictitious force. Let's look at some examples.